Hi, this is Tzvi Rosen here with another lecture on the history of calculus. And in today's lecture, we'll talk about the great Leonhard Euler. We'll start with a short biography. Euler was born in 1707 in Basel. That's in Switzerland, which we discussed at length when talking about the Bernoullis. He began studying math with Johann Bernoulli at the University of Basel in 1720. You'll note he was only 13 at the time, but that wasn't that unusual in that era. So he got his PhD, and he applied to teach at the University of Basel, but he wasn't accepted there. Then two of the Bernoulli sons, Johann Bernoulli's sons, Daniel and Nicolaus, they went to St. Petersburg, where there was a big push to develop the academy into a center of the sciences. And Nicolaus died shortly after arriving there, so Daniel called Euler to see if he would join and take Nicolaus's position, and that's what he did in 1727. And he stayed in Russia for most of his career. This is with the exception of extended stay in Berlin from 1741 to 1766. He moved to Berlin because he was invited, but also because he was invited by an institution there, but also because there was some political instability at the time in Russia that he was seeking to avoid. He had some serious health crises over the course of his life. He went blind in his right eye in 1738, and then his left eye in 1766. You might think that being almost entirely blind would have slowed down his mathematical output, but he was still publishing at a crazy rate. At his peak, he was doing about a paper a week. And he continued working until his death in 1783. He died in the middle of a conversation about the details of some astronomical phenomenon. Euler is regarded by many as the greatest mathematician of all time, certainly top five, just an astounding genius with contributions in every topic of math. If you want, you can check out the Wikipedia page for a list of mathematical concepts named for Euler. This is just a sampling, and it touches on geometry and calculus and differential equations and algebra, combinatorics. His reach was just absolutely unreal. And this is only a partial list, and I encourage you to explore that page. But today we're going to be focusing on his contributions to calculus. And something that might seem basic, but was actually a huge change from how things were treated previously, was his introduction of the concept of a function as a fundamental object in math, meaning something that accepts a variable as input, makes some transformation, and gives an output. Previously, like people like Newton and Leibniz, they thought about calculus as being a subject to be studied in the context of curves. But Euler was one who insisted that really we're talking about functions. And he was very creative with his functions, including allowing infinitesimals as inputs to his functions. So he would talk about things like sine dx. Okay, and discuss how to approximate this. He would say this is equal to dx. Okay. Another important contribution was to develop the math around the exponential function e to the x. He played freely and creatively with analytic formulas without necessarily keeping them related to the underlying geometry. So the sine function for him was mainly a power series. And he didn't have to think about them in the context of triangles or circles. And that also allowed him to input complex numbers, meaning numbers involving the square root of -1, into sines and cosines, because for him they were algebraic operations. And in this lecture, we're going to focus on a few particular contributions. We'll talk about Euler's magic formula, an integral of Euler, and particularly one that's presented in lovely detail in William Dunham's book, the Calculus Gallery, which is the source for most of our exposition, an approximation of pi, and the solution to the Basel problem. Okay, so we'll start with the Taylor series of e to the x. So Euler defined the exponential function e to the x as the limit as n goes to infinity of 1 plus x over n to the nth power. Okay, so to understand what the power series is, we want to work from that definition to prove that we're talking about the sum of x to the n over n factorial. Well, Euler's approach was to expand using Newton's binomial series. So if we have 1 plus x over n to the n, that's going to be equal to 1 plus n choose 1 x over n to the 1 plus n choose 2 x over n to the 2 plus n choose 3 x over n to the 3, etc. And this is 1 plus n times x over n. And you could also write this n over 1 factorial plus n times n minus 1 divided by 2 factorial times x squared divided by n squared plus n minus 1 n minus 2 divided by 3 factorial x cubed over n cubed, etc. And now the key is to apply the limiting operation. So the limit as n approaches infinity of this expansion, well, this will be, you'll have a bunch of cancellation. As n gets large, these polynomials approach the ratio of their leading coefficients, and in all of these cases, that ratio is 1. So they just drop out together, and we're left with 1 plus x over 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial, etc. And that was Euler's reasoning behind the Taylor series for the exponential function. Okay, so given that we have this power series for e to the x, and we know through geometric arguments or whatever other arguments the Taylor series or power series for cosine x and sine x, we can try to relate them to e to the x. So we have cosine x is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial, etc. And sine x is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, etc. And e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial, etc. So you can see all of these e to the x terms show up with some sign in the cosine and sine series. So how can we get the cosine and sine out of this e to the x formula? Well, the key is to consider what happens when we plug in ix, okay, and see what happens when we allow the square root of negative 1 to play a role. Okay, so we're going to set I to be equal to the square root of minus 1, and we're going to see what happens with e to the ix. So this is going to be 1 plus ix plus I squared x squared over 2 factorial. Now I squared is minus 1. So we're going to put this minus sign in here and have x squared over 2 factorial. You know, I'm going to just keep track of this computation. I squared x squared over 2 factorial plus I cubed x cubed over 3 factorial plus I to the 4th x to the 4th over 4 factorial plus I to the 5th x to the 5th over 5 factorial. And now at this point, I'm going to make it clear what these reduce to. So this is minus 1. This is minus I. This is 1. And this is I. Okay? So now we can extract out the complex and the real parts and the imaginary parts of this, the real and the imaginary parts of this series. We have 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial, etc. Okay, and that's going to cycle like that. Plus I times x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, etc. Okay. Now this can clearly be seen to be cosine x plus I sine x. So we have e to the x equals cosine x plus I sine x. Let's write that here. Okay. Now we can take x to be some nice values of x. So let's let x equal 0, pi over 4, pi over 2, and pi. So when x is 0, we get e to the I times 0 is 0, which is equal to cosine 0 plus I sine 0. Well, we know that cosine of 0 is 1, and I sine 0 is 0, so this is just 1 equals 1. That's not particularly magical. How about pi over 4? So we have e to the I pi over 4 is equal to cosine pi over 4 plus I sine pi over 4. Both cosine and sine of pi over 4 are 1 over the square root of 2. So we get this is equal to 1 plus I divided by the square root of 2. Okay. So that's cool, though we don't have reason yet to suspect that this is super interesting. Let's plug in e to the I pi over 2. This is cosine pi over 2 plus I sine pi over 2. Well, cosine pi over 2 is 0, and sine pi over 2 is 1, so this tells me that e to the I pi over 2 is I. And this formula in the line above it can now be reinterpreted to say that, well, the exponential is the square root of the exponential in the next line, so this means that the square root of I is equal to 1 plus I over the square root of 2. And indeed, running the squaring operation shows you that that's correct. Okay, but let's take one final value here, x equals pi, and we get e to the I pi equals cosine pi plus I sine pi, and sine pi is 0, cosine pi is minus 1, so we're left with e to the I pi equals minus 1. Rephrasing a bit, you have e to the I pi plus 1 equals 0. And this is the celebrated Euler's magic formula. Okay? And it just shows a willingness to experiment, to take an algebraic formula that you get in a somewhat principled way and see what happens when you plug in interesting values. You know, what happens when I take the square root of negative 1 and put it into an exponential? Nobody had thought of that before. Nobody had reason to think of that before. But Euler came along and showed how this unbelievable beauty could come out of that experimentation. Okay, so now let's take this integral that William Dunham highlights in his book, The Calculus Gallery. So we're going to integrate from 0 to 1 the function sine of ln x divided by ln x dx. And Euler's idea in approaching this integral, so if you take a calculus student, let's say you give them this integral, ask them to do it, they might try u substitution. They might try, some kind of dividing up the interval of integration to look for some kind of symmetry. But they wouldn't have so many tricks in their toolbox that they could use here. But Euler's idea was to treat ln x as an input into a Taylor series expansion for sine. So we know that sine of x is equal to x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, etc. So Euler's idea was to say sine of ln x, well, that will just be ln x minus ln x cubed over 3 factorial plus ln x to the 5th over 5 factorial. Okay, and take that further. And what happens when we divide by ln x? Well, this ln x becomes 1. This ln x cubed becomes ln x squared. But we still have 3 factorial here. And this becomes ln x to the 4th over 5 factorial. And continues out. Cool. So you might remember from one of the Bernoulli lectures that the integral from 0 to 1 of the nth power of ln x dx is minus 1 to the n factorial, minus 1 to the n times n factorial. So the integral from 0 to 1 of this function dx, well, that might be equal to the integral from 0 to 1 of its corresponding power series expansion in terms of the ln x's. So then we get this sum of integrals. So we have 0 to 1 of 1 dx minus 1 over 3 factorial times integral of ln x squared dx from 0 to 1 plus the integral of 1 over 5 factorial integral 0 to 1 of ln x to the 4th dx. Okay, now if we apply our fact from above, this becomes, so we have x from 0 to 1 minus 1 over 3 factorial times negative 1 squared times 2 factorial plus 1 over 5 factorial times negative 1 to the 4th times 4 factorial, etc. And what comes out of this is this beautifully concise infinite series. We have 1 minus a third plus 1/5 minus 1/7, etc. And this is the famous Leibniz series. Which, as you remember from our series on Leibniz, is equal to pi over 4. So the result of this messy integral, by applying power series and integrating each term of the power series, we arrive at a beautiful, concise solution. Okay, so that was one example of Euler's incredible talent for integration. He had contributions, as I said, all over math, and one of them was giving a great approximation for pi. So, as we recall in our lecture of Archimedes, Archimedes' approach to approximating pi was to use the method of exhaustion by taking regular 3 times 2 to the n-gons, like equilateral triangle or hexagon or 12-gon, etc., up to, I think, 96-gon, and to use geometric tricks to compute the area of those regular n-gons, and use that to approximate pi. The problem with that is you have to take a lot of square roots to apply Archimedes' geometric tricks, and square roots are messy. They introduce inefficiency to the process. It takes a long time to compute square root to high accuracy, and especially when those square roots are nested, the first approximations of the square roots need to be super accurate if the later approximations have a chance of being accurate at all. Then we saw Leibniz's series, 1 minus a third plus a fifth, etc. And this is a series which does give you pi over 4, but the rate of convergence is incredibly slow. You need billions, trillions, very large number of terms before you get even a few decimal places of pi. Okay, so there was interest to approximate pi in a way that you could add a few terms of an infinite series and get quite close to the actual value. And that was Euler's strategy, or that was Euler's goal, and his strategy used the following ingredients. He had the Taylor series for arctan of x, which is x minus x cubed over 3 plus x to the fifth over 5, etc. And he had a trig identity, which is tan of alpha minus beta is equal to tan alpha minus tan beta over 1 plus tan alpha tan beta, and you can derive that using basic Euclidean geometry. Okay, so his first step was to reformulate this trig identity. So we're going to reformulate this trig identity by plugging in special values for alpha and beta. And for alpha, we're going to take arctan of x over y. And for beta, we'll set arctan of z over w. And the reason for this is we want the tan to cancel with the arctan, and so we'll be left with a nice fraction on the right-hand side of the equation. So this gives us tan of arctan x over y minus arctan z over w. And that's going to be equal to tan of arctan x over y is just x over y, minus tan of arctan of z over w, just z over w. And on the bottom, we have 1 plus x over y z over w. Okay. Multiply top and bottom by wy to get xw minus yz divided by wy plus xz. Okay. And then, since we have a composed function tan of arctans, a combination of arctans on the left-hand side, we're going to apply arctan to both sides. And that will simplify things. So we get arctan of x over y minus arctan of z over w equals arctan of xw minus yz divided by wy plus xz. Okay. And now, so we're going to want to approximate arctan, like one simple arctan in terms of a combination of other arctans. So we're going to rewrite this as arctan of x over y is equal to arctan of z over w plus arctan of this messy fraction, xw minus yz over wy plus xz. Okay, so why is this useful to us? Well, Euler's idea is to take simple arctans, like we know that arctan of 1 is pi over 4. Okay, so that's a very simple expression. But because 1 is far from 0, the center of the power series, this is going to be a bad approximation, or slowly converging approximation. So we want to turn this into something where we're taking arctan of something smaller, so that we'll get a better convergence rate. Okay. Better convergence rate. Okay. Again, we're going to be starting with something like arctan 1 and eventually getting towards arctan of, let's say, 0.1 or something small enough, close enough to 0 that the convergence will be better. Okay, so we're choosing some nice constants, and this is what Euler did. So we're starting with all of the values 1 except for w equals 2. So we have arctan of 1 over 1 is 1 equals arctan of 1/2 plus arctan of 1 times 2 minus 1 is 1 divided by 2 plus 1 is 3. So we have 1/3. And what is the result? Or if we were to simplify this further, we would find that arctan of 1, as we saw on the previous page, is pi over 4, is equal to arctan of 1/2 plus arctan of 1/3. That's cool. Okay, so if we were to expand arctan of 1/2 and arctan of 1/3 and add those together, we would get pi over 4. But those values still aren't quite small enough to converge quickly. So we're going to use some different constants. Okay, how about the constants on the next line? Well, we have arctan of 1/2. Okay, that's something we saw in the previous line. This will be equal to arctan of 1/7 plus arctan of, so 1 times 7 is 7 minus 2 times 1 is 2, so that's 5, divided by 2 times 7 is 14, plus 1 is 15. So we get arctan of 1/7 plus arctan of 1/3. So now these two quantities, arctan of 1/2 and arctan of 1/3, can both be used to express arctan of 1/7 and arctan of 1. Interesting. How about the next line? Well, here we have arctan of 1/3 is equal to arctan of 1/7 plus arctan of xw is 7 minus yz is 3, that's 4, divided by yw is 21 plus xz is 1, that's 22. So this is arctan of 1/7 plus arctan of 2/11. Okay. So we've seen arctan of 1/3 and arctan of 1/7 before, so great. So we're getting different expressions involving these quantities, and now we're going to get something else, another expression to expand arctan of 2/11, this will be equal to z over w, that's arctan of a 7th, plus arctan of this fraction, which is xw, that's 14, minus yz, that's 3. That's 11, so 14 minus 11 is 3, divided by yw is 77, plus xz, which is 2, so that's 79. Okay, so it looks like that can't be reduced any further. So now we have, if we were to try and replace our original formula for pi over 4 using very small quantities, well, we could swap out the 1/2 for the expression arctan of a 7th plus arctan of a 3rd. So now pi over 4 can be expressed in terms of arctan of a 3rd and arctan of a 7th. Now you can swap out that arctan of a 3rd with arctan of a 7th and arctan of 2/11. So now we're just using those two quantities. But then we can swap out arctan of 2/11 with arctan of a 7th and arctan of 3/79. Now we have arctan of 1 will be some formula involving these arctans of very small numbers. Okay, and this is the precise formulation after doing all the arithmetic there, that pi will be equal to 20 times arctan of 1/7 and 8 plus 8 times arctan of 3/79. Okay, so how could I construct that? Well, we know that arctan of 1/7, that's going to be, we have the Taylor series up here, x minus x cubed over 3, it's plus x to the 5th over 5, etc. Okay, so we have 1/7 minus 1 over 7 cubed, 3 times 7 cubed, plus 1 over 5 times 7 to the 5th, etc., plus 8 times 3 over 79 minus 3 cubed over 3 times 79 cubed plus 3 to the 5th over 5 times 79 to the 5th, etc. Okay, and this is very simple series, and it converges very rapidly because each term, these are close to geometric series where the ratio is 1/7 of 3/79. Those are incredibly small. And if you use just up to the x to the 11th terms in each of these arctan series, then you get an approximation for pi that's off by just 2 times 10 to the minus 9. So it's really incredible accuracy. And Euler said this took him maybe an hour to do, as opposed to, people like Archimedes who were estimating with the method of exhaustion, where it would take them days, months, years to get accurate approximations for pi. So, as they say, work smarter, not harder. Okay, and the last contribution we'll see from Euler was his solution of the Basel problem. Now, we've discussed in previous lecture, I believe Jacob Bernoulli, one proof of the fact that 1 over n diverges. Well, it was known quite early on that the sum for n equals 1 to infinity of 1 over n squared is convergent. It approaches some finite sum, but the precise value of that sum was unknown. That is, it was unknown until Euler. And Euler started with a lemma. So let's suppose you know that you have an equation between an infinite series and an infinite product. Okay? How we could come to that equation with these two massively infinite objects? Unclear, but suppose we know that that's the case. Then the sum of the alphas, the roots on the right-hand side of the equation, in the product, that will be equal to a, the coefficient of x on the left-hand side. And the sum of the squares of those alpha k's will be equal to a squared minus 2b. And he had formulas for each of the sums of powers of the alpha terms. Amazing. So how did he arrive at that set of equations? Okay, so let's prove it. So we have this equation 1 plus ax plus bx squared plus cx cubed, etc. And then we have on the right-hand side this product. Okay. So how can we process this to make it a little bit easier to work with? Euler's idea was to do a logarithm followed by differentiation. Together, it's often called logarithmic differentiation. Okay, so we have a log on this side. Okay, it doesn't give us too much insight. But on this side, when we take a log of a product, that becomes a sum. So we have a log of 1 plus alpha k x. K goes from 1 to infinity. Okay, and now let's take the derivative. This becomes a ratio of series. So this becomes a plus. So basically, we're taking the derivative of a log is the derivative of log u is u prime over u. So on the bottom we have 1 plus ax plus bx squared plus cx cubed, etc. And on the top we have a plus 2bx plus 3cx squared, etc. Okay, so we have that ratio. And on the right-hand side, we have this sum, k equals 1 to infinity, of alpha k divided by 1 plus alpha kx. Okay. Next, Euler used what he knew about geometric series to expand each of these summands. So we have sum from k equals 1 to infinity of a geometric series. So 1 over 1 plus alpha kx is, and then multiplying by alpha k, well, let's keep alpha k out here. Then we have 1 minus alpha kx plus alpha kx squared, so alpha k squared x squared, minus alpha k cubed x cubed plus etc. These are all, this is just a geometric series with ratio minus alpha kx. So let's combine it to be k equals 1 to infinity of alpha k minus alpha k squared x plus alpha k cubed x squared, etc. And now Euler had the idea, instead of summing up each alpha k at a time, so summing up according to each k index, instead let's sum it up by powers of x. Okay, so this expression plugging that in here, this expression can also be written as the sum of the alpha k. So that's all of the single x terms minus the sum of alpha k squared x plus the sum of the alpha k squared, alpha k cubed, x squared, etc. Okay. Interesting. So now we have a power series where each of the coefficients is an infinite series. Okay, so now let's pull back this ratio. Oops. Okay, so this is going to be equal to this expression. Okay, so how can we take advantage of that? Well, if we want everything just to be in terms of power series and not ratios of power series, we can multiply both sides. And I should make a point here that this isn't really allowed. None of this is really allowed. Euler was just incredibly creative, and when he had the right intuition and he had beautiful algebraic analytic arguments, it didn't really matter that you shouldn't be able to do normal arithmetic on this stuff, because the arithmetic worked and it was beautiful. And that's the real charm of Euler's mathematics. It kind of somehow, despite the odds, it just worked. Okay, so let's multiply it. Let's cross multiply, and we have a plus 2bx plus 3c x squared, etc. This will be equal to the product of 1 plus ax plus bx squared, etc., times the sum of the alpha k's, and I'm going to leave off the indices right now, minus the sum of the squares, etc. Okay. So now let's compare the linear, the constant terms of this series. So on the left-hand side, we have a, and on the right-hand side, we have the only constant term in this product is going to be coming from the product of the constant terms. So this is going to be the sum of the alpha k's. Okay, and looking back here, that's exactly what we have in our first line. Okay, how about the linear terms? Okay, on the left-hand side of the equation, we have 2b. And let me just borrow this for a moment. I'm going to put this on the bottom here. So the linear terms, we have 2b on the left-hand side. And on the right-hand side, you can get linear terms by multiplying constant from here by linear here, or linear here by constant here. So we get minus the sum of the alpha k squareds plus a times the sum of the alpha k's. But we just learned what the sum of the alpha k's is. That's a. So this is minus the sum of alpha k squared plus a squared. Okay, and just rearranging the terms here, what this means is that the sum of the alpha k squared is precisely a squared minus 2b. Okay. Now let's consider the quadratic terms. Okay, so on the left-hand side, we have 3c. That's the coefficient of x squared. On the right-hand side, we're going to get 1 times the quadratic term, which is going to be sum of alpha k cubed, plus the product of the linear terms. Oops. So that's going to be a times that sum, plus b times the sum of the alpha k's. Okay, so let's write that up symbolically. So we have the sum of the alpha k cubed plus, or rather minus, a times the sum of the alpha k squareds plus b times the sum of the alpha k's. Okay, fortunately, we've already done some of the math here, and we know that, okay, well, we don't know what this is, but we know that the sum of the alpha k squareds is going to be a squared minus 2b, and the sum of the alphas is just going to be a. Okay? Just making a bit of room. Okay. Now to solve for alpha k cubed, the sum of alpha k cubed, okay, I'm just going to bring everything over to the 3c side. So we get a cubed plus 2ab, actually that should be minus 2ab, minus ab plus 3c, and that is a cubed minus 3ab plus 3c. Okay, and let's see what we have for that expression. Exactly, a cubed minus 3ab plus 3c. And you can see how you would do this for the succeeding terms, but if you start out with an equation of this form, of the form this infinite series equals this infinite product, then you can use that infinite product, or you can find really concise formulations of the infinite series associated to the coefficients in that infinite product. Okay. Cool. Well, we're going to now argue that, and this was Euler's genius yet again, like, this shouldn't work, but why not? We're going to argue that a certain function can be expressed both as an infinite sum and an infinite product. And that function is, for us, is going to be cosine pi over 4x plus sine pi over 4x. Now, the fact that it's infinite sum shouldn't be surprising because we have the Taylor series. We know this was well known by the time of Euler, that this would just be the sum of minus 1 to the n pi x over 4 to the 2n, or pi x to the 2n over 2n factorial 4 to the 2n, where n goes from 0 to infinity. And by the same token, sine pi x over 4 will be equal to the sum, where n equals 0 to infinity, of minus 1 to the n times pi x to the 2n plus 1 divided by 2n plus 1 factorial, 4 to the 2n plus 1. Okay, and this is just basic. But let's write out the first few terms for completeness, and because it'll be useful for us. Let's make this a bit smaller. Put this here. Write this again. Okay. So let's write out the first few terms. So p of x equals 1 plus pi x over 4 minus pi x, or pi squared x squared over 2 factorial times 4 squared. Okay, then the cubic term will be from the sine series, pi cubed x cubed over 3 factorial 4 cubed. And let's do one more, plus pi to the 4th x to the 4th over 4 factorial 4 to the 4. Okay. And it will continue that way. So we have our infinite series. How about an infinite product? Well, we want to, in order to express this as an infinite product, the first thing you have to do is make sure that wherever p of x is 0, your infinite product will also be 0. So when is p of x equal to 0? So then you have cosine pi x over 4 plus sine pi x over 4 is 0. Well, let's subtract cosine x from both sides, or subtract sine x from both sides. Why not? So that means minus sine pi x over 4, and this if and only if, minus sine pi x over 4 equals cosine pi x over 4. And now let's divide both sides by cosine. And we find that minus tangent pi x over 4 is equal to 1. Okay, well, the tangent function is pretty well understood, and I'm going to actually just erase that minus and put it over here. This means that pi x over 4 should be equal to arctangent of minus 1, which is minus pi over 4. But this is only one solution to the function tan pi x over 4 equals minus 1. You can get other solutions by just adding integer multiples of pi. So this is for n in z, the expression minus pi over 4 plus n pi will work. Taking this result to the next page, we have pi x over 4 for values of x where p of x equals 0 have to be equal to minus pi over 4 plus n pi. Another way of writing this would be pi over 4 times 4n minus 1, where n is an integer. Okay? So dividing both sides by pi over 4, we get x must be equal to 4n minus 1 for n an integer. And this set of values is, if we start with n equals 0, then 1 gives us 3, minus 1 gives us minus 5, positive 2 gives us 7, minus 2 gives us minus 9. And you'll see the pattern quite quickly. These are the odd numbers with alternating sign. Okay? Cool. So if these values of x make p of x equal to 0, then when we expand p of x as a product, so we're going to say p of x will be equal to, we want to make sure each product vanishes when you put in the corresponding 0. So when I put in x equals minus 1, this vanishes. When I put in x equals 3, I want this to vanish. Okay, and you'll see that we're basically putting in the reciprocal as the coefficient of x, or the minus reciprocal as the coefficient of x. 1 minus x over 7, then when x equals 7, that term vanishes, etc. Okay? So another way of writing this is that our sequence of alphas, we have alpha 1 equals 1, alpha 2 equals minus a third, alpha 3 is minus positive a fifth, alpha 4 equals minus a seventh, etc. So we're getting all of these reciprocals of odd numbers with alternating signs. Cool. Okay. So now, without a ton of justification, we're going to say that this is the infinite product formulation for p of x, where that is our p of x. So now we have an infinite sum and an infinite product. So let's see what results from our lemma. The first result of the lemma is a equals, okay, so let's just cite the lemma. A equals the sum of the alpha k squared. Sorry, not squared, just the alpha k. So let's look back what our a term is. That's going to be pi over 4. Okay, so this is pi over 4. And what's our sum of alpha k's? Well, that's the sum of these terms. 1 minus a third plus a fifth minus a seventh. Wouldn't you know it? We have our Leibniz series yet again. Okay, so that's a nice confirmation that this, or at least evidence that this equation of series and product actually holds. And that means we just want to apply the next one to solve the Basel problem, the next part of the lemma. So we have the sum of the alpha k squareds equals a squared minus 2ab. So a, as we just saw, is pi over 4. And b is minus pi squared over 2 factorial 4 squared. Okay, so taking a squared minus 2b, we get pi over 4 squared minus 2 times negative pi squared over 2 factorial 4 squared. Simplifying, the first term becomes pi squared over 16. And the second term becomes, well, the 2's cancel, the minuses cancel, and we're left with pi squared over 16. So their sum is pi squared over 8. Interesting. What about the sum of the alpha squareds? Well, this is going to be given by 1 plus, and now the sign alternation doesn't matter since we're squaring all of the terms. So we're just going to get 1 over 3 squared plus 1 over 5 squared plus 1 over 7 squared, etc. So this sum of squares of the reciprocals of odd numbers is equal to pi squared over 8. Cool. But we really want to know what the sum of the reciprocals of all squares are. So let's write out an equation. We have S all, meaning the sum of the reciprocals of squares of all the integers. Okay, and then on the other hand we have S odd, which will just be the sum of the odd numbers, 2k plus 1 squared, where k goes from 0 to infinity. And we have S even, which will be 1 over 2k squared, where k goes from 1 to infinity. Okay, so the first thing that pops out here is that obviously if you sum up all of the reciprocals, it's going to be equal to the sum of the odds plus the sum of the evens. Okay, and we know from the lemma and from the computation above that the sum of the odds is pi squared over 8. Okay. On the other hand, looking at the form of S even, I can extract a factor of 1/4 from every term, and what's left is S all. Okay, so because S all, S even is equal to 1/4 of S all, we get pi squared over 8 plus 1/4 S all. And subtracting 1/4 to the other side of the equation, we get 3/4 S all equals pi squared over 8. And multiplying both sides by 4/3, we get S all, i.e. the sum of the reciprocals of the squares, where k goes from 1 to infinity, will be equal to pi squared over 6. Okay, and this is truly a magical equation, perhaps even more so than Euler's magic formula. This was the solution that evaded Jacob Bernoulli when he was computing sums of series. And Euler managed to get at it just using this freewheeling, perhaps unjustified, but undeniably creative and beautiful manipulations of series and products. Okay. In conclusion, Euler was among the greatest mathematicians ever, perhaps number one. He applied the tools of the calculus developed in the preceding generation in incredible and creative ways. Most notably, he used power series creatively to relate exponential functions and trig functions and to approximate pi. As with the Basel problem, though, sometimes his methods were not well justified, and we're going to see some backlash to the lack of justification in some of the uses of the calculus in our next lecture about Berkeley and his critique. Thanks very much.